Good morning to Dr. Nurshia. We are from Group 3 and going to present about the elements in Group 13. Meet our team. I'm Varshni going to present about the physical and chemical properties of Group 13 elements. Munjia Hao going to present about the applications of the elements and the effects towards the environment including plants, animals and humans. And while SKT3013 is going to give a brief introduction about the elements in the group.
I am SKT3013 binti Darmansha. My matric number is D202110999330. In this video, I'm going to introduce about element in the group 13, which are boron, the symbol is B, aluminium, Al, gallium, Ga, indium, In, and thallium, Tl. They are characterized as a group by having 3 electrons in the outermost part of their atomic structure. Boron, the lightest of this element, is a metalloid. Aluminium, gallium, indium, and thallium are silvery white metal. Boron is a very rare element. It mainly occurs as orthoboric acid, borax, and kyanite. The abundance of boron in Earth crust is less than 0.001% by mass. Aluminium is the most abundant metal and the third most abundant element in the Earth crust at 0.3% by mass after oxygen and silicon. Bauxite and chloride are the important mineral of aluminium. Gallium, indium, and thallium are less abundant elements in nature. Boron was known to ancient Egyptians in the form of mineral borax. It was not until 1808 that the metalloid was known in its pure form when Humphrey Davy was able to extract it by electrolysis. Next, aluminium was first known in mineral before it was finally extracted from alum. Antoine Lavoisier and Humphrey Davy had each separately tried to extract it, but neither succeeded in doing so. Many attempts followed by various scientists, but none succeeded in extracting pure aluminium. The first pure sample of aluminium was found by Harry Antoine Clay Deville. Thallium was discovered by William Crookes and Claude Auguste Lamy in 1861 when they were examining residue from sulfuric acid production. Indium is the fourth element of the boron group but was discovered before the third gallium and after the fifth thallium. In 1863, Ferdinand Rich and his assistant Hieronymus Theodor Richter were working in a sample of the mineral zinc lens, also known as sulfuric, for the spectroscopy lines of the newly discovered element thallium. Gallium was first predicted to exist by the creator of periodic table, Dimitri Mendeleev, in 1869. In August 1875, French chemist Paul-Émile Lecoudé was pondering.
Now I'm going to present about the physical properties of Group 13 elements. The first property is atomic and ionic radii. The size of an atom is defined as the distance between the nucleus and the outermost electron. It depends upon the number of shells and screening effect of orbitals. Generally, down the group, the atomic size increases because new shells are added at each step and effectively nuclear charge decreases. Atomic and ionic radii of Group 13 elements are lower than those of alkaline earth metals of Group 2, primarily due to greater nuclear charge of Group 13 elements compared to Group 2 elements. On moving down the group, the atomic radius of gallium is slightly lower than that of aluminium. This is due to the presence of d electrons in gallium which do not shield the nucleus effectively. As a result, the electrons in gallium experience greater force of attraction by the nucleus than in aluminium. Thus, the increasing order of atomic radii of Group 13 elements is boron to gallium to aluminium to indium and to thallium. Moreover, the atom's ability to attract a bonding pair of electrons is called electronegativity. Thus, the electronegativity first decreased from boron to aluminium, then it increased slightly from aluminium to thallium. This can be attributed to the poor shielding of the intervening end of d and f orbitals. Decreasing order of electronegativity of Group 13 elements is from boron to thallium to indium to gallium and to aluminium. Then, the ionization enthalpy is defined as the change in the enthalpy which is associated with the removal of the first electron from the isolated gaseous atom present in the ground state. So, it requires energy to remove the electron from the isolated gaseous atom. As shown in the table, so while we move down the group, that is from boron to aluminium, the ionization enthalpy decreases because the atomic size increases as well as the screening effect also, which has the ability to outweigh the increased effect of the nuclear charge. But from aluminium to gallium, the ionization enthalpy increased slightly. The first ionization enthalpy of thallium is greater than the aluminium. Next, I'm going to explain about the density of group 13 elements. Boron and aluminium have relatively low densities, whereas the higher members have high densities like gallium, indium, and thallium. The densities of group 13 elements are higher than those of group 2 elements. Due to higher effective nuclear charge, the ionic and atomic radii of group 13 elements are smaller than those of group 2 elements. As a result, the densities of group 13 elements are higher than those of group 2 elements. Density of group 13 elements increases in going down the group. This occurs due to the more closely packed structure of higher elements of the group. In addition, the melting and boiling points of group 13 elements are much higher than those of group 2 elements. It is due to the stronger interatomic attractions in these elements. The melting and boiling points of boron are very high as compared to those of other elements of the group. This is due to the network structure of boron. Gallium has the lowest melting point in this group due to the weak binding forces in the system, which gallium acts as Ga2. The elements of this group exhibit high boiling points, which steadily decrease in going from boron to thallium. Now I'm going to explain about the chemical properties of group 13 elements. First of all, reactivity of group 13 towards oxygen. All of the elements of group 13 react at high temperature forming trioxide, which is M2O3. Here is the equation of the reaction of oxygen and a group 13 element. 4 mole of M element reacts with 3 mole of oxygen gas to produce 2 mole of M2O3, where M is any group 13 element. At high temperatures, thallium also reacts with oxygen to produce thallium oxide. The most common oxide form of boron, B2O3 or boron trioxide, is obtained by heating boric acid. Aluminium occurs almost exclusively in the +3 oxidation state. It rapidly reacts with oxygen in air to give a water-insoluble coating of aluminium oxide. This oxide layer protects the metal beneath from further corrosion. Next, reactivity of group 13 elements towards acids and alkalis. Boron does not react with non-oxidizing acids like hydrochloric acid, but at higher temperatures, it reacts with strong oxidizing acids like a mixture of hot concentrated sulfuric acid and nitric acid. Boron resists the action of alkalis such as sodium hydroxide and potassium hydroxide up to 773 Kelvin above, which they form borates. All the other elements of group 13 react both with non-oxidizing and oxidizing acids, liberating hydrogen gas. The action of concentrated nitric acid renders aluminium and gallium passive by forming a protective layer of oxide. Aluminium and gallium can also react with alkalis, liberating hydrogen gas. Now, reactivity of group 13 elements towards halogens. They react with halogens at high temperatures to form trihalides, which is MX3. The reaction shows that 2 mole of M element reacts with 3 mole of X2 gas to produce 2 mole of MX3, where X is fluorine, chlorine, bromine, and iodine. Thallium, however, only forms thallium fluoride and thallium trichloride. Thallium also forms monohalides. In addition, reactivity of group 13 elements towards water and metals. Firstly, reactivity towards water. Boron does not react with water or steam. However, at very high temperatures, it reacts with steam. If the oxide layer is absent, aluminium decomposes cold water to yield hydrogen gas. Gallium and indium do not react with water unless oxygen gas is present. Thallium forms thallium hydroxide in moist air. Next, reactivity towards metals. Only boron combines with metals to form borides. The rest of the elements of group 13 are reluctant to combine with metals. This portrays the non-metallic character of boron. The reaction shows that 3 mole of magnesium reacts with 2 mole of boron to produce 1 mole of magnesium boride. That's all from me. Thank you.
Applications of group 13's elements. Boron is used in fiberglass, ceramic, and in leaches in the form of borax. Aluminium is used in everyday life. It is used in utensil and construction material. Aluminium is a component of alloy that are used in the making of lightweight bodies for aircraft. Next, gallium has application in semiconductors, amplifiers, solar cell, and internal diodes. Other than that, indium is also used in solder, heat reflector, phosphor, nuclear control rod, and solar panels. Next, thallium can be found to be used in low melting glasses, photoelectric cell, and switches. Thallium is also used in vermin killer rat and mouse poisons.
Thank you, Talina. Now, I would like to explain about the effect of group 13 elements towards environment, which include animals, plants, and also humans. First of all, in general, boron has a low toxicity to humans and animals. Instead, it can make up with oxygen and sodium to form sodium tetraborate. And the powder detergent is considered a least toxic recipe as a natural disinfectant and household cleaner. However, it can be harmful if ingested in large quantity. Too much of boron can cause reproductive problems in both humans and animals, as well as skin irritation. Next is aluminium. Large part of both the aquatic and terrestrial ecosystem are affected. In the aquatic environment, aluminium acts as a toxic agent on gill-breathing animals such as fish and invertebrates by causing loss of plasma and hemolymph ions leading to osmoregulatory failure. The third element is gallium. Although gallium is not a harmful in small amount, but it should be not purposefully consumed in a large doses. Some gallium compounds can actually be very dangerous. For example, acute exposure to gallium trichloride can cause throat irritation, difficulty to breathing, chest pain, and its fume can cause even very serious conditions such as pulmonary edema and partial paralysis. Furthermore, gallium is also used to hold some nuclear bomb bits together. The plutonium then becomes unstable in fume because the gallium is corrosive to several other elements. If the gallium is removed, however, the plutonium becomes useful again. But the process of remove the gallium contributes to a huge amount of pollution of water with radioactive substances. The next element is indium. So in the rapid growth of new electronics and energy technologies require the use of rare elements of the periodic table. For many of these elements, humans are not really know about their environmental behavior or human health impacts. This is true for indium and gallium, two technology critical elements. Increased environmental concentration of both indium and sodium will create the potential for increased environmental exposure. The evidence is mounting the indium and gallium can have substantial toxicity, including in occupational settings where indium lung disease has been recognized as a potentially fatal disease caused by the inhalation of indium particles. Last but not least is thallium. So, thallium can affect human nervous system, lungs, heart, liver, and also kidney. If large amount of thallium are eaten or drunk for a short period of time, temporary hair loss, vomiting, diarrhea can also occur, and death may result after exposure to large amount of thallium for short periods. As in humans, animal studies indicate that exposure to large amount of thallium for brief period of time can damage the nervous system and heart, even can cause death. Lastly, here is some reference which our group find for doing this teaching video. That's all from us. Thank you for watching.